Just in time too.
Yeah, yeah, and you can grab some. Okay, welcome everybody to New Star and to SFPUG September meeting. We're going to get started with a little lightning talk here. CK Tan is going to give us a lightning talk about a just-in-time executor. He'll explain what that is. And after we have the lightning talk, I will do a few announcements. We change speakers, and then we'll have the main event about HyperLogLog tonight. And talk about everything then. So, go ahead.
Hi. Hi everyone, I'm CK. We just started the company with Castella, and we have a prototype that I'm showing you right now. It's a JIT compiler that compiles your query and then run it. Compiles the query into LLVM and then just run it. And the performance is quite spectacular. So let's start. So why do we do this? So the Postgres executor is using, we all know it's 30-year-old technology. It's an iterative style of pool model. You know, you got a query tree and you just pull a tuple from your child, and your child pull another tuple from its child, right? And that leads to a lot of branch instructions, a lot of indirect calls, and a lot of non-local control flow. So because the tuple needs to travel from the bottom to the top. It's okay in the old days when everything is IO bound, and it's not so good today, right? Memory is cheaper. Almost everyone has their database that fully fits in memory now. IO is cheap too, right? And we are getting more and more CPU bound. I think this will last less than 5 minutes. So how do we do this? We take the query plan that Postgres gives us, and we generate LLVM code based on the plan. Right. So we use a push model where a row, when you in the bottom is going to be a scan, right? When you get the row in, it's going to deformat, which essentially already puts the whole thing into registers, and then the next operator will immediately run on top of those registers, and then the next one until it has to be pushed into memory. Right? Until the point where you hit a hash join or something like that, that you must write to memory. The advantage of generating the LLVM code is you eliminate a lot of branches, right? Because you know that this is a scan node. I don't need to know, is this a scan node? And do this, dereference this virtual function call and call that. It's all known when you compile the plan. And variables, a lot of variables becomes constants. Code is very small, very tight, and it avoids a lot of intermediary read and writes to memory, because between operator nodes, if you don't need to write to memory, you just push up to the next level in registers all the way up until it needs to go to. If we cannot generate the plan, if we cannot generate the LLVM code for any reason, we probably haven't implemented everything. We don't do we don't do calls into Python or something like that. We would just punt it to the PG executor. So this is essentially a drop-in product. If you have a query that it can help, it will generate the plan and it will generate the LLVM code. It will run it and you will see performance. If not, then it will be just like within our resources. Yes?
What sort of increases do you see on what kinds of classes of query?
So to compile the LLVM code, to generate and compile the code, it takes about 10 milliseconds. So it doesn't make sense if your query is very small and tight. It doesn't make sense if you do a single tuple retrieval, right? But we can probably know that by looking at the cost model created by the planner and decide whether to go this route or that route.
Seconds or milliseconds?
Milliseconds in compilation. But the stuff that this will help most is when we have a complicated query, or we have an analytics query. Okay. So I have some performance number. So we're seeing this performance number on a Core i7 gigabyte 3x4 boxes. So that's the first number. It's query number for TPCH. So Q1 runs in 2,702 milliseconds in Postgres. Okay, and it only runs it like 305 milliseconds when we were able to compile that. So we're seeing, so Q1 is a simple hash ag. You scan line item, aggregate it, and print out the server, right? So something like that, it's 9 times. And in general, it's about 3 times.
Does the second row include compilation time?
Yeah, that's all included. So next I can. Are we up for 5 minutes?
Just keep going.
Yeah, finish up.
It's done. I can do some demo now. Can you see? It's not. So this slide, I'm echoing the. So on the left side, it's just a tail of the PostgreSQL. On the right side is where we can run the query. So if we run something like this, it's patient. So query like this is it's an aggregate on line item with the 6 million rows in it, and with a qualifier and a sum. So it takes like 473 milliseconds in this case, right? Quite consistent. So I can do this. So now it's going to run it in Postgres. And something that we don't handle like this. This is a window query in Postgres. Some simple stuff like select stuff. So when it's really simple, it's about twice the performance.
Do you catch the...
Awesome. Thank you very much.
Okay.
The startup. So will we get set up? So will we get set up. I have your usual set of announcements. So welcome everybody to San Francisco Postgres User Group September meeting. For whom is this your first SFPUG meeting? Wow, a whole bunch of people. Okay, so you in the back row over there. If you want to just stand up real briefly, say your name and how you use Postgres.
My name is Ashish, and our company is Postgres. I actually am not touching that question yet, but function is that. So, that's all I can say.
Okay, welcome. And we had a whole row of people over here. You probably came in together, so pick one of you. Yeah? No? You didn't come in together?
Yeah, no. No, we're here for fun.
Yeah? So how do you use Postgres?
It's my favorite destination.
Awesome. And we had a couple of folks over here. Who was new over here? Okay. So you in the plaid shirt.
My name's Rafael. I work at Newstar, and I use Postgres for a lot of things. Most recently, it's a pretty simple web server with no user interface and API. I think.
Yeah. Wow, cool. Welcome. So, first of all, I want to start out by thanking our hosts and food sponsors here, Newstar. So thank you guys. And then say a couple of things that are going on currently. Number one, does anybody know where Postgres 9.4 is? Has anybody seen Postgres 9.4?
No way, you lost it.
Yeah, right. Right, we've got it in the sides of milk cartons now. So, how many people here downloaded and tested the 9.4 beta? Well, a few people. But the rest of you didn't. And that's why 9.4 is not out yet. It is your fault. Because in late August, somebody found out that we had a serious problem with the file format for JSONB. And so we're testing solutions for that now, but that's delayed the release. And we don't want to actually release with this problem because once it's out there, people are not going to want to change the file format for their in-place data because that would require rewriting all your tables. So that's delayed the release. I've talked about the sum. It's the whole issue of the original JSONB data was just really not compressible at all, which would be a problem for people who have lots of big JSONB blobs. That's been corrected, but now that means that we're looking at sometime in October for the release of 9.4. So and if anybody here has actually put data into 9.4 beta, has anybody put like data in 9.4 beta? Just so you know, you're going to have to rewrite any data that went into a JSONB field.
I knew that
when you did it, yes, when you did a beta, yep. So we got some other stuff coming up. Well, actually, we just had Postgres in Chicago, Postgres Open. Anybody go to that? How was it?
My presentation was good.
Yeah, awesome. Yeah, terrific. Stuff we have coming up. Next month is Postgres in Madrid. So PGConf EU. Anybody going to that? We have a big travel budget. There we go. Awesome. Have fun with Postgres in Madrid. And more, sort of bringing it a little bit closer to home. There will be a couple of things coming up in the new year, just so you can think ahead. Number one is we will have a Postgres Day at Southern California Linux Expo in February, as we always do. For any of you who are going to scale anyway, or a business that takes you down to Los Angeles. I don't know if the date is that, but it'll be on the Friday before the main conference. The second thing that's actually been a recent development is FOSS4G, the free and open source geographic conference, whose general attendees are big PostGIS users. They will be having their North American conference in March in Burlingame. And so we are planning to have a full day of Postgres something there. Details to be determined, but just something for you to be thinking about. And when the details are confirmed, I'll probably be hitting people up to speak and or sponsor that event. Next month, so far what we have on the calendar next month is almost exactly a month from today. One of our Google Summer of Code students is going to give a presentation about his Google Summer of Code project. I'm trying to remember which project was his. But anyway, he's come all the way up here from Brazil. and he's going to be talking about the project that he worked on for GSOC, Hacking Postgres. And that's going to be next month. The other thing that will be coming up soon that we're still trying to nail down the timeline for is we're going to be restarting ValleyPug. So how many of you are here from the South Bay? Okay, actually only a couple. So that'll be of more interest to people who are not currently here. And that's pretty much what we have coming up. Does anybody else have any other community type announcements? Or, you know, for that matter, people who have sponsored or hosted an SFPUG in the past are welcome to make things like job announcements. If you want to make a job announcement and you haven't sponsored or spoken, I'm willing to talk to you about sponsoring future events.
Always be hustling.
Yeah. Okay. Well, so then we're ready.
Okay.
So Timon is going to present all about HyperLogLog and why it's something that you should have already known about.
Yeah.
So take it away.
Thank you. All right. Is that a more reasonable line? Everybody hear me? Good. Great. I'm Timon Carnizos, Director of Infrastructure at Neustar. And basically this talk is about sketches and databases and why sketching algorithms are running in your database and why you should be using them more explicitly to do things like analytics in a much more, shall we call it, agile way. You can iterate more quickly on analytics and do more interesting things in smaller memory and so on and so forth. So I just have one question to throw out there. In Postgres, is count distinct on a billion rows hard or easy? Okay, all right. How much memory does it take to do count distinct on a billion unique rows?
It can take very little memory and a lot of disk.
Okay, fair enough. Well, let's say a billion rows. Let's say you can hash them all uniquely to big ints. That's 8 times a billion, which is 8 gigs. So keep that number in your head as a contrast to what I'm about to sell you, which is should feel like a Virgin Brooklyn. So I'm going to take you through a rough idea of what sketching is. We'll talk a little bit about the history of HyperLogLog, which is kind of one of these extremely impressive sketches and is considered kind of the pinnacle, in a way, of a class of algorithms. We'll talk about our own implementation of that data structure as a Postgres extension. And finally, I'll haphazardly throw a bunch of links at you for further study if you have the time or interest. So let's talk about what sketching is. And I will first wave my hands and be a little hand-wavy about these definitions. Obviously, there's a ton of mathematical formalism around every highlighted term I use in here. I'm going to avoid that by and large, just so I can get the idea across. Hopefully, it instigates you to go read and figure out what that mathematical formalism translates into. So, there are really two terms that we have to talk about in terms of sketching: probabilistic algorithms and streaming algorithms. So, when we talk about a streaming algorithm or the streaming setting for an algorithm, we're talking about a set of constraints on what that algorithm can do. Specifically, 3 things. 1, you have to use some sublinear memory and often fixed memory. And sublinear means if I have a billion things to count uniquely, then I should be using far, 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 far less than a billion bytes or what have you, or a billion machine words. You only get 1 pass over the data, and in whatever order it comes in, you don't get to sort the stream. And then finally, your updates have to be constant for roughly constant time. You can't spend too much time on any piece of work. So that's streaming, right? And we can think of a couple of very silly streaming algorithms. Min and max being easiest. Obviously, they satisfy the small memory constraint, 1 machine word. They satisfy the in order, out of order constraint, right? Because you'll always find the max no matter how you show me the stream. And finally, there's 1 comparison and optionally 1 write every time. So that seems pretty constant to me. You can think about something a little bit more subtle, like the mean of a stream of integers. But that's really just 2 machine words, the sum and the count, numerator, denominator, right? You move along with your life. So hopefully that gets you in the mindset of what we're trying to do, and that we're trying to apply that to count distinct. So then we have this other side of the equation, which is the probabilistic algorithm side. And again, this is where I'm going to hand wave the most. What I'm talking about here is algorithms that take that take reproducible randomness and inject them into the formalism in order to smooth out the average case in order to get better average case behavior. And in some cases, this means that the algorithm can tolerate error, meaning it can give you an answer that is a little bit off some percentage of the time, right? So you can think of it as an epsilon delta trade-off, right? You have an epsilon that says up to a factor, I'm going to give you a slightly wrong answer, and that error bound is going to hold some percentage of the time. And I think something that we can all wrap our head around a little bit is, as a probabilistic algorithm, is an open addressing hash map, in fact, because there are hashing collisions, and because of those hashing collisions, you have a variable number of steps before you find the actual thing you're looking for. So hopefully that can get your head in that space. Now, when we put peanut butter and jelly together, we get sketching. And so by and large, this is a really broad class of algorithms, and I'm going to focus on a much smaller subset, specifically ones that give you an approximate answer, meaning that epsilon kind of constant factor error, and some delta, which basically says, hey, we have some probability that you'll get an answer within that error bound, and outside of that time, outside of that probability, you can get either a completely wrong answer, I can opt to give you no answer, right? So this gives you the rough bounds of what I'm trying to do. The last thing that I want to talk about is additivity, which is kind of a nice to have. Not all sketches satisfy this property, but the best ones do, so to speak. And this means if I have a stream A and stream B, and I run them through two different data structures, and then I run stream A plus B through a third data structure, I have some way of combining sketches A and B to look exactly like the one that had both streams run through it, right? And this is a really useful property. We'll get to it a little later. So I'm going to anticipate some people's concerns here, which is that, hey, we have perfectly good things like hash sets or sorted lists that will tell us very well exactly how many distinct items you have in there. But I will just point out that unless you're saving lives or worrying the billing code of your application, you often don't really need an exact answer, and often the difference between a perfectly correct answer and a just good enough answer is about 1,000,000% memory savings, and that's a joke, so actual 1,000,000%. Thanks to JD for pointing out that number to me earlier. So in this way, these sketching algorithms are astonishingly painfully useful to us in the analytics world. So I just wanted to set that out there. This isn't for your banking code. This is for your analytics code. Okay. So let's get into the history of streaming a little bit. We're going to go back to a magical year, 1983, really a mythical year, if you will. And you have these two fellows, Philippe Flageolet and Nigel Martin, chit-chatting. Nigel is doing RDBMS research in the 70s at IBM. And so obviously databases were a new thing then, and the whole idea was, as you know, we're trying to give people access to data and run queries on it without knowing the structure of the data per se, or not knowing statistics about the data. It's automatic. So they think about query planning. Well, what do we need to do to be able to plan a query? Well, some of these simple queries need selectivity estimates. If I apply a predicate to a column, is it going to get, how many rows is it going to give me back, so that I can chain my predicates together so that I get the most selective first, so I have to scan fewer and fewer rows. And finally, what they realize is, hey, a really primitive way of understanding selectivity is understanding the cardinality of a column in relation to its total size, because then you can just divide one by the other and say, hey, if I'm going to hit this range, then I can multiply the selectivity estimate against that range and see roughly how much I have. So that's how we get into this talk, basically. There's this algorithm in 1983 that presages and eventually leads up to HyperLogLog, and I just thought it would be really fun to talk to a group of people who love databases about something that's already in your database in just another format. So the whole premise of this algorithm is that I can count to n uniquely, meaning I can do a count distinct over a domain that has size n. So imagine, in 1983, that's usually 2 to the 32, and who needs more than 2 to the 32 integers, whatever. It's saying that I can count to 2 to the 32 uniquely with just log 2 of that many bits, which in this case is int 32. So remember what we said earlier about a billion things taking about 8 gigs. If you had a perfect hash set that had no collisions, it would take a minimum of 8 gigs to store. Well, they're claiming that they can give you an estimate in 32 bits. So that seems like a pretty good improvement. So they basically claim that the intuition that you'll need to understand this paper is as follows. If I go and stand behind your back and start flipping a coin, as many times as I would like, without telling you how many times I flipped it, and then I come back to you and say, the longest run of heads that I saw in my coin flipping was 10 heads in a row, right? I saw it at some point, at least once. Then my question to you is, how many times did I flip that coin on average, right? And if we assume a fair coin, then you think to yourself, well, a string of heads, 10 long is 1/2 to the power of 10. That's the probability. You saw it about one time. If I kind of abuse any notion of probability, of rigorous probability, we're going to say 1 over 2 to the 10 times what equals 1, 2 to the 10. So I'm going to estimate that you, in fact, saw, or that you flipped the coin at least 2 to the 10 times, right? And this is the intuition we'll need to understand how to count things distinctly. I'll take you through that. So, in order not to fill up this slide with way too many things, I'm going to assume our big N is 2 to the 8 here, which in this setting means that I'll have 8 bits to work with. And I'm also going to assume I have this magical object, h of v, a good hash function. And what I mean by that is that for our domain D, so our 2 to the 32 integers, 2-bit strings of length L, where L is usually large enough, but in this case has to be at least 32, whose output are uniformly random, meaning the bit strings that come out really don't depend in any way on the input, except for that they are reproducible. If I put the same thing in twice, whatever, I'll get the same answer out. It's a hash, cool. So here are my 8 bits. What does the algorithm say to do? Well, it says first, hash and value your bit string. So I did that. V of 0 is 1 and then 7 zeros. Next thing, figure out the lead run of zeros. And since it starts with a 1, that lead run is at length 0. And what I do is I mark that in the bitmap. I say, I have seen a run of length 0. Okay, mark it as 1. Then I do it for another one, right? And its run is of length 1, so I'll mark the 1 in the bitmap. And then say 4, I'll mark the 4 in the bitmap. So now that you're effectively done with that, if you wanted to estimate the cardinality of this string, what you could do is you could basically find the leftmost 0. So, or alternatively, you can think, what's the position after the smallest position such that everything to the left is 1, right? Whatever, same difference. And so I'm going to pause here for a moment and just say, you should be starting to have the aha moment with the flipping of the coins, right? That seems pretty straightforward. What I want to point out is why the distinctness works. Because if I put the same value into this hash function, it's going to have the same run of zeros up front. If it has the same run of zeros, I'm going to mark the same bit. And that bit is either 0 or 1, so it's not going to change. So I can put the same value in as many times as I want, and it's not going to change what my data structure is, which means it can't change the answer. So what do we do once we found the index of the first 0? Well, we basically call it I. We do 2 to the I over phi, where phi is some correction constant, which is about 0.773/1, and you get your answer. So in this case, the real answer is 3. We got 5 out, not the end of the world. And frankly, it's a neat trick in log 2 of n bits. And if we think about this a bit more, you might be thinking to yourself, well, in your example with flipping coins, you said what was the longest run. And in this case, the longest run would have been at index 4. And the reason why we don't do that is anytime you introduce reproducible randomness into an algorithm, you're going to have to deal with these outliers or what have you. You're basically going to have to cull out all these things that randomly got thrown out really far to right field. So what they do is they say, well, there's some notion of density that everything to the left of the second position, or index 2, is full, so that will kind of control for these random outliers that set bits far to the right in the bitmap. So it's a cool algorithm. If you're thinking that it's going to be off by some, yes, Ben?
They're not really outliers, right, though, because the hash function is random, so you expect these things to be,
yes.
You expect equal chance of you having outliers as
Yes, in fact, I kind of posed it in a narrative format, but you do expect, so in essence, we're trying to control for this, and by finding the dense part of the bitmap, you're effectively saying, aha, this is a pretty clear way of saying, I've seen everything in between here, which means that this will be a better estimate of how many unique things I've seen. And this brings up a good point, which is, well, you expect these things, so you expect error, and what is the factor that I'm going to be off by here, roughly? We're talking about binary. Somebody say 2. Okay, it's 2. Why is it 2? Because if I just get one thing that, if everything is nice and compact and I have nothing off to the right, and I put one more thing in there that sets the next bit, then I'm off by a factor of 2 automatically because I'm saying 2 to the I where I is the index. So I think what's really cool about this algorithm is that, one, the authors totally acknowledge that this is the start of something. In fact, the reason why Philippe worked with Nigel Martin on this was because he found it to be such a powerful and novel technique. And Nigel brought this intuition to the table, and Philippe brought this incredible rigor in mathematical knowledge. I mean, he was truly a titan in his field. He's the biggest name in the analysis of algorithms, short of Knuth. In fact, Knuth shouts out to him constantly because he died in 2011. And he has the ACM conference on discrete algorithms has a whole track named after him. So this guy was serious business, and he was extremely smart, and he brought a huge level of rigor to these things. So that constant wasn't empirically determined; it was analytically determined. So if any of you have done complex analysis, then you'll know that it's not all fun and games, and it's quite hard to do that. So they acknowledged that there was a problem with what they built. They're saying, hey, this is a cool first step, and of course, being diligent as they were, they improved on it. And what they did is they came up with probabilistic counting with stochastic averaging in 1985, 2 years later. And their argument was, hey, if one of those bitmaps is off by a lot, what happens if we keep a lot of those bitmaps around and we average their answer? Will that be better? And in fact, the answer is yes. And the mathematical formalism is called stochastic averaging. And basically they argue, if I take my stream and hash it to a bunch of substreams, and then for each substream, keep one of these bitmaps, and then basically go through when I want to do the same thing as we talked about before, but when I want to figure out what the cardinality is, I go find the leftmost 0 in each one, I find the index corresponding to it, I average those indices together, and then I do that same exponentiation that I showed you earlier. It does, in fact, provide a better answer, way better. In fact, the error bound went from off by an order of binary magnitude to something like 0.78 over the square root of the substring count. And this is relative error, so 1 would be that it has 0 error. So 1, if I put the substring count in there, or excuse me, 0 would be 0 error. So the idea is if I increase the substring count, thereby increasing my memory requirements, I end up reducing that number, and I can get closer and closer. So in this case, if I got it down to 0.01, for instance, if I evaluated that, got down to 0.01, I could expect 1%. Okay, great. But Philippe obviously did not stop there, because this is talk about HyperLogLog, and we haven't talked about that yet. And in 2003, he and one of his students, Marianne Durand, worked on this idea of, well, hey, instead of trying to control for these outliers or these random bits that get set far off to the right of the bitmap, maybe what we could do is eschew the bitmap entirely, just pick that longest run. So instead of a bitmap of 32 bits and that m times, all I need is something that's 5 bits, because with 5 bits I can count to 31, right? And I can mark the highest set index. And then using this, I can do a better estimation using that same exponentiation and averaging. And if you think about this, this is a pretty big coup. We've gone from our basic register being a bitmap of size 32 times some number of substreams, and that's log base 2 of n. And we've gone to log of n, which is tiny, right? 2 to the 64, log base 2 of that is 64, log base 2 of that is 6, right? So we're talking about tiny little things, right? And you're going to think to yourself, oh, okay, that's cool, but you're going to introduce more error. But the nice thing is, hey, now your registers are 6.4 times as small, which is fantastic, right? Because if we're talking about 2 to the 32, I have 32-bit registers, log base 2 of that is 5, right? 32 divided by 5 is 6.4, right? So 6.4 times smaller, so I can keep that many more registers, right? And what does that effectively mean? Well, I get this new error bound, and this new error bound looks like it was worse than before because it used to be 0.78. But in fact, I have 6.4 times more registers, which means that square root works out, and you get a much better answer. So this is great, fantastic. And just to give you a look behind the scenes of the making of these algorithms, obviously, people make algorithms, right? Robots don't make algorithms. Well, maybe now they do. But the point being, there are people behind this, and there's a lot of humor, and there's a lot of humanity in the process. So we actually met up with one of Philippe's grad students after Philippe's death, and corresponded with him and got him to help us with some of our problems with HyperLogLog, and he gave us some of the color behind all this. So he provided us a draft of the LogLog paper with Philippe's notes to Marianne. And as you can see, Marianne has used Maple to get a better formula for this integral, which of course Philippe was not having at all. And actually, you think, okay, he's French, and that would be pronounced Jesus, right? In fact, no. He loved cussing in English, apparently. And he may be the only French person who liked cussing in English. So this is kind of indicative of both his humor and his level of formalism in terms of the rigor he brought to the table. So you know, it's kind of sad, on a side note, that he passed away in 2011, basically right exactly when industry started picking up his algorithms for wide adoption, which is kind of sad, but so be it. So they do some work here, right, and they actually get something better than PCSA, probabilistic counting with stochastic averaging. They get this thing called LogLog, right? It's much smaller error, it's really impressive, but it doesn't end there. There's just one more thing. In 2007, a group led by this guy named Giroir, with Philippe's help, figure out something even better. They basically keep the data structure identical to LogLog, and they improve the mean, the way to average the register values to compute the final, what they call the indicator function, the final cardinality estimate. And so instead of doing the arithmetic mean of those registers, which allows those, what we call the outliers or whatever, to play a big part in what the value is, they use the harmonic mean. And the harmonic mean is the, I always forget this, it's the reciprocal of the arithmetic mean of the reciprocals of the register values. And so what it does is it's this nice, really nice smoothing out function. Effectively, it diminishes the value of these much, much higher registers and lets the true kind of core of the register values have more impact. And so this led to much, much, much tighter error bounds, which is really elegant. So we had 1.3 over square root whatever, and now it's 1.04 over the square root whatever, and it turns out to be pretty much information theoretically close to the best you can do in the entire distinct values estimation game. So that's where we land. And sadly, like I said, Philippe, titan of his industry, passes away just before this happens to come out. And this is really kind of the gold standard for streaming algorithms right now. There's no bigger name in streaming algorithms than this. So I will stop boring you with theory, and we will talk about, yes?
I actually have a question about the theory. So don't these estimates make the assumption that the distribution of values is random?
No, it doesn't. That's what the hash function's role plays. So the hash function maps what could be a very dense space into a very sparse space by their construction, in a sense. So that's exactly why you need a good hash function. Because if you have, let's say you have the values 1, 2, 3, 4 through 10 and 100, right? A good hash function will not map 1 and 2 adjacent to each other in the hash space, in the output space.
Right, no, but I'm actually talking more about skewed distributions.
Okay.
Like, I mean, let's say that your stream was actually what political party do Americans belong to, right? You can have a whole lot of Democrat and a whole lot of Republican and a tiny amount of anything else, right? So the fact that you have a run of Democrat or Republican is not as significant as having a run of...
no, so you misunderstood. Yeah. So the Democrat would be encoded, let's say, as, like we'll pick a byte, right? There are 88 parties in the US, right? Each party gets a value, so 0 through 7, right? 0 is going to be hashed into our, say 32-bit space, way far away from anything else. So I really only have 8 things to count.
Right.
The runs of zeros is the runs of zeros in the bit string produced by the hash function, not in the stream itself. So if I go back here, right, I'm saying if the first value in my stream was v0, I'm hashing it, and the hash outputs a bit string, and I'm looking at the runs of zeros in that bit string, not
in the hash,
yes,
not in this.
Yes,
in these sweet values.
That's correct.
Okay.
Yeah. So, like I said, there's hash functions are magic. I'm going to give you a link later on to a talk given at the University of Copenhagen in August at this summer school of hashing. If there's anything you want to know about hash functions, you will get an answer there. It's unbelievable, so I encourage you. But where was it? Okay, so enough theory, unless there are more questions. Okay, great. We'll talk about our implementation. I'll take you through what the code looks like, some of our design decisions, a couple of examples. I'll do a standard data brag about how much data we have. And then I'll take you through the lessons learned in building one of these extensions, specifically as it relates to building an extension that has a sketching algorithm. So what is the extension? It's called HLL on GitHub. It's Postgres HLL, whatever. It's a handful of C. It's some SQL to kind of bind it together to Postgres. It's a bunch of comments. There's a hashing algorithm in there that's pretty good. And then we have a crap ton of test vectors. So not much going on. You can practically ignore the SQL. It doesn't do anything except for wrap the C functions. So we'll get into what the C does. There's the obvious stuff, which is, yes?
So you mentioned C++, and that makes me a little hinky because anytime C++ throws an extension or an exception, Postgres can become very, very unhappy.
I did not know about that, but having put this thing in prod for a while now and not having run into anything of that sort, okay. I mean, I certainly, if somebody has a C version of Murmur 3 that is output and input compatible with the Java one, tell me, I'll switch it in a heartbeat. Because we have all the test vectors that will tell us if we did it right, so that's good. So anyways, the code has basically some marshalling to and from by day formats. We kind of piggyback along what Postgres provides for by days. We have some bit slicing code to slice up the hash values and to update the registers because we have bit packed registers. We have a formula for cardinality, otherwise what good is this, right? And then finally, remember that additivity thing I talked about? We have code that will push two HLLs together, and all that code is the pairwise max of the registers, and it outputs a new HLL. So that's not so fancy. I'll tell you a little bit about why we built this and what the design was centered around. So basically, we wanted to count the number of unique people who saw an ad, and that required basically three things. It had to be small, we had to be able to combine it, and the approximation couldn't be too bad, so to speak. So I'll address the first one. How did we make it small? First of all, we're going from like 8 gigs down to a couple of kilobytes for count distinct on some stream. So that's great, awesome, fantastic, but we wanted to do better. Our environment is highly skewed. So we have a few ads that get a few impressions, or we have lots of ads that get a few impressions and a few ads that get billions of impressions, meaning there are billions or hundreds of millions of people that saw those ads. So what we wanted to was, by and large, to store these ads that didn't see many people much smaller than the kilobytes it took to store the data structures for those that had seen billions of people. So we have a header, and that header is like a token for the empty sets. So those get smaller. Up to a certain point, we'll just store it as a sorted list of big ints, those hashes, and then the hierarchy progresses. Once it gets big enough as a list of big ints, then we switch it back to a sparse hash map of register index, register value for all set registers. And once that gets too big, because there's overheads to that, we flip to the full representation of usually 5 bits times 2 to the m divided by 8, so 2 to the m minus 3 bytes. So practically, I'll tell you a bit more about that, but just know that this whole thing goes from 3 bytes to a couple of kilobytes to do pretty good estimations of count distinct. The next thing was the additivity. So I'll point out one thing, that the union, because it has this additivity property, kind of preserves the error that you've chosen, right? You pick a number of registers, how much memory you're willing to devote to this, and that grows or shrinks the error depending on how few or how many you decide on. So if I combine 2 streams together, they should have the same error because I have the additivity property. And what having a lossless union allows you to do is to do set difference and intersections via inclusion-exclusion principle or basic set algebra, which is incredibly useful. And I can't emphasize this enough. Like, hey, it was very, very hard to do things like rolling windows of count distinct because you had to keep rolling over those 7 days of data or whatever. They want the last week's unique counts by day with a 7-day rolling window. That's hard because you have to scan 7 days, 7 times. And now all we do is we have one data structure and we just union it with however many we want, right? So this is cool. I have the star next to set difference and intersections, and you just have to be incredibly, incredibly careful with these. The union preserves the relative error that is guaranteed by the paper. Set difference and intersection do not. It's nonlinear error propagation. So, I've written a pretty extensive blog post on this. I'm not going to try to cover it here, but I will link you to it. at some point, I think. And we'll just cover kind of, I'll mention it, and in that blog post is covered kind of what type of error propagation you can expect. So you can do these things, you just have to be careful. And then finally, I'll tell you a little bit about the approximate nature of this stuff. So imagine you're using 2 to the 14 5-bit registers. That's 81,920 bits, 10 kilobytes. So in 10 kilobytes, I can get about a 1% relative error. So if I'm measuring something that has 1 billion uniques in it, 1% of that is 10 million, so my absolute count will be off by 10 million. And you might think, oh my God, you're off by 10 million. That's galling. I hate that. I don't like you. And I say to you, if I told you as somebody who is purchasing ads on the internet that your ad got seen by 1 billion people or 1.01 billion people, would that sway you to not buy or buy ads? And the answer is no. Because swayed by that. They're like, holy crap, 1 billion, that's great. We should show more ads, right? And so this is kind of the stuff we work with. And that drove our design decision. Basically, we knew we had to be in the kilobyte range because we keep hundreds of millions of these around. And so I'll tell you a little bit about that in the data brag section. And I want to take you through a couple of examples. Obviously, we have way more examples online on our blog posts and what have you. And if you want, you can just email me with your problem, and I will happily write you a SQL to solve it. So imagine we have this table, which is a day, how many page views you had that day, and then an HLL of how many unique cookie IDs were seen that day. What if you just wanted a report that told you how many uniques you saw? Well, any standard ETL plus Vertica or whatever, or maybe even Postgres or Hadoop or whatever can give you this answer, right? And the way we do that is by putting that hash operator in front of any HLL column, and that is a shorthand for compute the cardinality of that HLL and spit it out as a double. Think about it. Or sorry, a floating, or maybe it actually truncates it to an integer. But in any case, that's how you do it, and you can get this pretty much with any analytics system. So this is not hard, right? This is really straightforward, and it looks pretty clean, right? What if, like I mentioned before, you wanted the cumulative number of uniques over a 7-day rolling window for the last year, right? Every day in the last year, I want you to tell me on that given day, plus 6 days before it, how many uniques you saw. Well, in a standard system, what you have to do, because of the nature of the problem, to get those uniques, you have to sit there with a 7-day window for every single day in the year. So it's 365 times 7. That's effectively how many days you're scanning in that process. And you're doing count testing for each one. With HLL, it's a lot simpler. You get to use those really nice window functions that Postgres provides, and you just set your window to the last 6 things. You use the nice HLL union aggregate function, which will union everything as an aggregate function, and then you put the hash in front of it, and you get your answer, right? So you can say the average frequency over the last 7 days, every day in this year was blah, blah, blah. Right? I find this incredibly impressive. Like, you couldn't do this type of analytics before without waiting days for something to come back. Or you had to be like Google and wrote Dremel. Right? Those were your options. You either had a bazillion machines to do it on, or you waited. And now you don't. And I think that's incredibly impressive. You can iterate on a report really, really quickly. And we've had this in prod for like 4 years. Like, you can iterate on a report very quickly with this. You can take somebody who's barely technical or somebody who knows SQL. You can take our VP of Engineering, Steve Lindy, and have him poke around in a database and design new reports and do analytics in seconds, right? He can go there and go through it and scan 1 million rows in 20 seconds and do uniques over that in the same amount of time. So I'm not going to belabor this point more. If you want more examples, go to ly/pghll. That's the blog post where we open sourced it. It has some examples in there. It has some cool product ideas if you want to go build a company. Yes, that. So I'll just go through the bragging rights thing really quickly. We run PG 9.3. Thank you, Matt Wood. It's amazing to have DB able to keep us up to date. Yes, sorry.
I didn't write down that for your
PG HLL. We use Postgres 9.3, which is amazing. We get to do neat things like copy to a table from a program, which saves us a lot of space. But anyways, on PG 9.3, on some actually kind of old embarrassing hardware, to shove millions of new HL elements. Do we have there?
depending on what we're looking at, the base number is 18 months.
Okay, so 18 months times millions per day, and we keep that in a single Postgres instance, so yay. You can HL union ag a million rows in 20 seconds and get an answer out of it. We built Java interop, basically storage, binary compatible interop between Java and Postgres, so that we can pass these things back and forth between the database and the application. And we've been doing this for 4 years. It works. It's a really great idea. Like I wouldn't do analytics without this stuff anymore. That's just my opinion.
So who else in the industry is using the meta? In your group, I mean, out there in the industry.
Well, Ben from Citus behind you encourages all of their users to use it, right? Or like you shift it to multiple
We
users.
use it for distinct approximation.
Okay, so
SQL queries to use. We do too.
And Adobe.
and Adobe, and then JD from GitHub uses it to do their user analytics. So a lot of people use this. Google has a paper on this. Facebook has a paper on this. It's built into Dremel. It's built into Presto. It's built into Redshift. It's built into Vertica. It's built into Oracle. It's built into Hive, Spark, Redis. Womp womp. Yeah, so that, I think a lot of people use it. It's kind of well adopted in that sense. It's well supported. We try to be good custodians of our open source, and it's kind of embarrassing. I got like 2 new tickets opened on our HLL projects today, so I'm kind of embarrassed about that. But nonetheless, I think this has great traction for one reason. The math behind it is super, super, super solid. Philippe's responsible for that. The ease of use these days and being able to sell it as agile analytics to your customers when they ask why is it off by a bit is really straightforward. Unless you're using it for like the most sophisticated use cases like doing intersections, you have to be a little more careful. But by and large, I think people say off by 1% is fine if I can get it in real time.
I don't want to settle down, I really don't.
Yeah.
This is the kind of thing that should have come out of Postgres years ago. Why didn't it?
Why didn't it? I think that's an interesting thought. I think to a certain extent, the whole sketching industry, the sketching academic world was highly focused on a handful of problems up until about 2007 or 8. It was focused on the internals of databases, so joint size estimation, selectivity estimates. You saw this stuff come up in routers, network hardware, estimating the number of unique flows to do DDoS mitigation. You saw it on the insides of packet switching systems to do real-time audits. Famously, so one of the researchers in the field, with Krishna, built a system at AT&T called Gigascope that monitored all of their net traffic using a handful of sketches. But this was all kind of highly operational focused, right? It wasn't an end user thing. So I can only attribute it to that in the sense that it was so highly focused in academia where it originated that they really didn't have great industry contacts. And I do mean to brag, sorry. So when we got a hold of this about 4.5 years ago, nobody was using it, and we were extremely confused. And we had a company called Aggregate Knowledge. That company got bought, so we were at Newstar now. But that was the whole basis of the company. We couldn't afford MapReduce then. Hadoop was immature, it was expensive, we didn't want to buy the hardware. So what we did is we built a real-time streaming system that did all these aggregations in memory, and HyperLogLog was the reason why we could do it. So it went literally screamed from the rooftops, and JD was around back in the day when we'd invite him to like these tiny little meetups and hope that 4 people would show up. And we would yell and scream about how impressive this stuff was, and nobody would listen. And then, 2 years later, Google drops a paper on HLL++. We made some changes to this algorithm. And it's all already shown. So I can't attribute it. I think it's long overdue. I think it's really awesome. That's the best answer.
So in other words, it was there. It just happened to take a big person, and suddenly everybody else said, "Oh, cool."
Yes, that's correct.
So you mentioned the internal databases.
Mm-hmm.
Do you see any possibility of having Postgres?
Yeah, so the question was, does it make sense to try to push HLL down into the guts of Postgres? And this is a fascinating question. It's the first one I asked myself after I got this, so very on point. The answer is it doesn't, unfortunately. There's been a ton of research in databases, as you can imagine, especially in query planning. And the sentiment from the researchers we've spoken to is that past about a 5 to 10% error, your query plans don't get better. Right? So being able to like squeeze it down to 1% or something on counting billions of things, just doesn't give you a better, faster plan at the end of the day. And so the low-hanging fruit is already gotten with a lot of these histograms, with a lot of these bitmaps that you see in databases, in just the statistics you pull out of the index.
I don't know, our indistinct estimation is considerably more than 5 to 10% off.
So the sentiment was that on the most sensitive systems, 5 to 10% was all you needed. So there's a paper from 1978 that basically states anything better than 25% is a waste of space. So, and it's part of the system R group of papers. The query planning in there was, rudimentary, shall we say, but they didn't see better results. And I really don't anticipate seeing better results. I think it's really neat. I don't know how useful it is. I think, and I don't know how much time I have left, but the notion is that there are other sketches that are more suitable for pushing into databases that do joint size estimation much better. And I think that's where the real value is. Really what you want is an approximate histogram that will allow you, that has additivity, one, and that has the ability to kind of do a dot product and guess how many things going to come out of that. So that's where my money would be if I were designing a database for that. But you can always go pester them and see if they use it for something more interesting. Wave.
The problem with indistinct estimation is limiting the size of the sample.
Yes.
There are lots of ways we could estimate indistinct if we were willing to read 10% of the table.
Sure. That's a great point, right? It's how much scanner I'm willing to dedicate to it. So, dry grant side, I'll just talk to you a little bit about building this thing and the pitfalls we ran into. So the first thing is don't use a cryptographic hash function. Please, it's not needed. And even if you think you do need it because, hey, we got to be private and secure, you actually don't. If you think about what's happening, I'm hashing it, I'm turning it into a bit string, I'm reading the length of zeros, and I'm putting that in a register. And even if it changes that register, there's no way you can back out enough information from a register flipping from 4 to 5 to de-anonymize whatever you put in there. So use non-cryptographic hash functions. A couple of great examples right now out there. Murmur is considered old news, old hat. They found problems with it. It works really well in production. We don't see any practical problems with it. I encourage you to look at city and farm and SIP hash as alternatives. Basically, any Mac works, but realistically, you want something that goes really, really, really fast on the data types you usually put in there. Strings, not that often. Mostly ints, big ints, floats, doubles, whatever. Yes?
Did you test Murmur compared to anything else, or was this just?
We did. We have a whole. I'll send you down a rabbit hole blog post that my colleague Colin Pacino wrote on picking a good hash function. So we went down the path of just like, hey, does it run good in prod, to everything down to the Kolmogorov-Smirnov test, which actually tells you, hey, is this not uniformly random, even though it looks uniformly random to every other test in the world. So we went down that rabbit hole. Yes, I'll give you the resources in a second. So one, pick a good hash function, right? Because it's very, very important to the success of the HLL or of the probabilistic algorithm. Don't mess with the inputs, and this is a war story for production. Imagine you're designing an A/B testing system, and you want to pick some users to put in the A group and some users to put in the B group. Assume that you have a random unique user ID that you give them. Well, why don't we just look at the last bit in that user ID and just say if it's 0, put them in A, and if it's 1, put them in B. Well, as it turns out, that means that you are basically depriving that one bit which is used in that bit string. So everything was off by an order of magnitude, or binary order of magnitude, because everything had one less 0 to start with in one group, and everything started with a 1 in the other group, so there were a ton of zeros in the other. So just don't mess with it. Hash it again. Use the other hash to do your A/B testing or what have you. So just don't mess with the actual bit string you're going to use that you're going to feed into the algorithm. I think rigorously unit test and fuzz test any interop you're going to build. You will find the craziest things. You will find out that the C++ Murmur implementation, when given a -C, produces different output when you give a -C to the Java implementation, even though they're written by the same dude at Google. You will find out about endianness. You will find out about storage formats on disk. Just put as many test vectors as you can into that thing and run it every single time you make a change. And then finally, leave crumb trails for yourself in your source code back to parts of the paper. Formulas, to diagrams, to assumptions, like keep a canonical annotated version in source control with your code. It is incredibly useful. You don't want to be debugging something and have to reread the whole paper for that one little thing you made an assumption. So that said, I just want to give a shout out to a bunch of people and lead you through some other resources that you might find useful if this was interesting to you. If you want to learn more about the history of streaming and Philippe Flageolet's contributions, Jeremy Logrosso has a fantastic deck that he presented at our Data Science Summit a couple years ago, and you can find that at bit.ly/Logrosso. If you want to see some really cool visualizations of different sketching algorithms, including HLL, go to Sketch of the Day. And thanks to Rob Brzezinski, Matt Kersey, and Ben Lindsay, who are my either current or former colleagues. Krishnan, again, this dude is like he's unbelievable in terms of intelligence. He also has, cornrows, and he's kind of a pudgy Indian dude. So he's a striking image. He's amazing, super smart. He has a book which you can find a copy of that is a kind of an overview paper, if you will. It's like 200 pages long of problems in the streaming and probabilistic space. If you want a good, quick PowerPoint to go through, Alex Andoni, who's a former researcher at Microsoft, researched Silicon Valley before they all got laid off a couple of days ago. Go to Andoni PPT, and you will find that great little presentation he gave. And if you want to see more about the physics of HLL, what you can do in terms of unions, in terms of taking something that has this many registers and making it smaller or bigger, my colleague Chris Henderson wrote some fantastic posts that I've accumulated under that URL. And finally, if you want to know how to pick a good hash function, this is the definitive set of stuff. Like we only put stuff on our blog when we actually used it for production purposes. These are our own resources, so they're good enough for us. Maybe they're good enough for you. We certainly refer to them all the time. That's the piece, thanks to Colin Pacino, who's actually a medical student who was not sufficiently challenged by med school, so does CS research for us. Finally, thank you to these wonderful people on GitHub for contributing to our 3 HLL projects. We're honored to have your engagement with our open source stuff. Thank you so much. And I'll put up this presentation. In the presentation, there are links to all these papers. This is kind of like a hyper-curated set of sketches, and it kind of goes through the history of probabilistic counting all the way through HyperLogLog. You get counting in Sketch, which is kind of this unbelievable sketch designed by Grant Cormode and Krishnan that lets you do things like have an approximate histogram. K-min values is another way to do distinct value estimation, which is also fantastic and a little more intuitive than HLL. And finally, majority was designed in '81. It's not technically a streaming algorithm, but it's about the coolest thing you could write with 4 lines of code. It will tell you if a stream has a majority element, meaning something that happens more than half the time. It will give that answer to you using exactly 2 words of two machine words and 2 comparisons, and it just blows my mind. It's like one of those amazing things that everybody should Google. Finally, semi-finally, go look at the notes and lectures from the DIKU Summer School on Hashing. Michael Thorpe organized it. His talk is fantastic. His set of talks are fantastic. Michael Witzenmacher, who's essentially the king of bloom filters and cuckoo hashes, his talks are unbelievable. One's a professor at Harvard, the other is a professor at the University of Copenhagen. They are amazing speakers. It's extremely clear. I encourage you to have videos as well as their notes. Just go read everything Michael wrote. And finally, if you know a way to make PostgreSQL, HLL, go faster, I will bribe you. Whatever magic you got, I will take it. We will make it worth your while. Anything that makes it go faster, whether it's SSD and SIMD, or whether it's something that you know about the Toast system, or something you know about marshalling, or whatever, tell us. I will buy you scotch. I will buy you whatever your poison is. Just tell me, please. That's it. Thanks. I'm sorry? I'll put them up on our blog, and I'll send them to Josh. Get them posted at their relevant place. Yes?
So you were talking about being careful with subtractions and intersections, right, as opposed to units.
Yeah, so set, where did I put it?
Set the difference.
Yes.
So, I mean, we're trying to use this actually, similar to what you guys are doing. And can you talk a little bit more about what kind of care needs to be taken?
So what care needs to be taken? So if you can imagine, let's talk about the intersection. So the way to get the intersection cardinality of 2 HLLs is to A, B, and A union B. You take the cardinality of the 3 of them and you use the inclusion-exclusion principle, which is cardinality of A plus cardinality of B minus cardinality of A union B. So that's 3 things that have 1% error, right? And what happens is, if, let's say B its cardinality is roughly the size of the error on A, meaning, let's say I have something that has 1 billion things and something that has 10 million. The 1% error on 1 billion is 10 million. So when I try to do that math, the entire size of B is going to get lost in the error of A. So the kind of good basic rule you can think about is, as long as A and B are roughly the same size and don't have very, very low overlap, which is hard to know a priori, of course, but as long as, in general, the things you try to compare are you're not trying to measure 1% overlap, that's the same idea, right? If your answer is roughly the size of the error of one of these things, it's going to be 1. So the notion is, if A and B are roughly the same size within a factor of 10 or within a factor of 7, right, you're going to get a decent answer. You're going to get what we call a directionally correct answer.
What about if they have low cardinalities? Because then you actually store the exact.
So then it's exact,
right?
Which is fantastic, right? So in the ad space, you have impressions, which are basically things people saw, which are the least valuable thing in the ad world. You have engagements, which are people who clicked, and there are about 1,000 times less of those than impressions. And then you have conversions, which is when somebody buys something and you get notified about it, and they saw an ad beforehand. So there's 5 times fewer conversions than clicks, right? So or conservatively. So what we're saying is there's a 5,000 to 1 ratio of the least important to the most important things. So for a given ad, if we can store, say, 500 things uniquely exactly, that's perfect. And we want to use that. We want to set the thresholds for our HLLs for conversions to be much, much higher because those are super valuable. I want to know what the intersection of that with other things. But for impressions, right, it's 1 billion against 900 million, and who really cares? Right? By and large, you're just trying to figure out, like, a great thing we do is we let you figure out if you see people on site A and site B, but you pay more for them on site A than you do on B, and you largely see the same people, you should be buying on site B, right? It's pretty straightforward lookalike analysis, what you call it, or lookalike audiences. And the idea is you can get a directionally correct answer. If I'm off by 10%, and the intersection is 80%, it's like, yes, you should be buying on other inventory providers. Like, I don't know what to tell you. Like, you know what I mean? Like, the answer is yes, and you're just, nitpicking about something that doesn't really matter in terms of your buying decision. So, that said, I think it's really useful basically to present these present HLL-based answers for. There's a lot of talk about like Lambda architecture, like you have a streaming component and you have a batch component. The streaming component goes for a while until the night finishes, and then you run the whole thing in a batch and you update if that counts. Great, hunky-dory, do that. That's usually my answer about these things. You just got to be careful. Like I said, you just got to make sure that your sizes are roughly the same, and if not, you present that fact to the user that they're not. You just grade out and say, hey, sorry, we can't give you a good estimate. But as it turns out, you're trying to find the overlap of something with 1 billion uniques in it, with 10 million. So even if you wanted to go change your buying habits and get those 10 million people for cheaper, it's not going to make a difference because you have 1 billion of them over here that you're paying. So that's kind of how we approach it. It's more of a UX problem. Steve?
So the problem is really good visualization that shows different set sizes and you're accurate.
Yes, totally. So if you go to so I don't think I have it on here, but if you go to research.newstar.biz and search for JS-HLL, there's a blog post that we put out when we open source the JS interoperable library, and it has this cool little visualizer that lets you, that shows you exact answers and approximate answers and does a neat little Venn diagram visualization. And it really makes clear because it will like shade the outer ring of what are the circles in the Venn diagram to demonstrate how much of that circle is error. And then you'll see that like a little thing just fits inside of the error. So it's good to play with to get a good sense of what that does. More than anything, I would just test this on your workloads. It doesn't cost that much. Just go create extension HLL and go fiddle around with it. My advice. Any other questions? Yes?
If you sort the input stream, it doesn't break the algorithm.
No, it does not. However, there's a fascinating algorithm that came out about a year ago called frugal streaming, which computes the median of a string in exactly 1 word of memory, which is incredibly simple. So what happens is, if you get an item in the string, and your current counter, which starts at 0, is less than that item, you increment your counter. If the item comes in and it's less, you decrement your counter. And over a large enough stream that isn't sorted, what will happen is you'll actually gravitate towards the median of that stream, which is crazy that a counter can then take on the value of the integers in your stream. So yes, there are things that will break. Most canonically, quicksort is actually a randomized algorithm, and it will break on sorted input. So that's a great question. In these cases, since they basically just use the longest run of zeros in the bit string, it doesn't matter what order you present. Yes.
You mentioned in your benchmark that it's 20 seconds to query a 1 million row table, but you had to populate it first, and typically when you're doing analysis, you're also generating a queue with dimensions like country, site, publisher, this and that. What's the cost of populating those HLLs and the
Well, I'll tell you. So back in the day when we were a scrappy startup, we had built our own custom in-memory streaming system to do this in real time, and then every night we take a snapshot of the previous day. And then that we had, again, binary compatibility between our snapshots coming out of the streaming system and the Postgres copy format. So you just directly load them into Postgres, and they'd be pre-built by Dietrich. And right, you get you just load them straight in, so it was no cost to us in a sense. Right now, that streaming trade-off, doing it all in memory, kind of ran into the limits of what you can do on one machine in memory, and now we build them with Elastic MapReduce. I don't know, like, so we do about, let's say, 300 gigs compressed 6x of input of raw data into our MapReduce system. We spend about, I'm not going to give away the secrets, but like we spend less than $100 a night to do one map step and one reduce step. It all happens in about an hour, and out comes tens of millions of HLLs. So I don't know, per HLL, like some fraction of a cent. You can build them in Postgres actually really quickly. So Steve Liddy ran a test a while back on some random QA hardware, and with hashes, so if you generate a random stream of stuff and then you hash it and then you insert it into Postgres HLL, you can get, because it's all in C or C++, you can get 2 million inserts a second conservatively. I've seen it on faster i7 hardware get up to 6 and 7 million inserts a second. So that's, if you have raw data and you're building it, I would be skeptical if you had that data in Postgres, but you couldn't build the HLL for it in under 5 minutes. No matter how you segmented it. I mean, really the biggest problem you'll run into is that, and this is a problem that we'll just run into, is that if you are doing a group by and Postgres decides to keep it in RAM instead of spilling to disk, the HLLs are really big, and I don't think Postgres accommodates for that really well.
The hashtag never spills. So
it's maybe a bug, who knows? Yeah. So this hashtag spills to disk, or never spills to disk, and so you run out of memory, and the out-of-memory killer goes and nukes your process. Which
yeah, well, I think we make the assumption that the values produced by the aggregate function are going to be approximately the same, within 2x of the same size of what produced them.
Right.
Which is probably a wrong assumption. I mean, it's probably something we should fix.
the other problem with our hashtag is that we have there are some analyses that are done that end up with very large cardinality in the group by. And so when you multiply that by the 2.5K that the HLL takes up in our production system, it adds up very quickly. And so what it'll do is it'll say, oh, well, I've got enough memory to do a hashtag, but then the cardinality is much larger. It ends up being 4 or 5 dimensions, much larger than the original spectrum. So you end up with a very, very large output. But that's the extreme case. That's not normal.
So you can build them really quickly unless you're one group by, and you can always segment it. You can basically go do it one day at a time, and then you'll output the HLLs, and you can output the union of the HLLs using HLL union add. So there are incremental ways to do it. I have not seen data sets on Postgres that use HLLs that are bigger than ours. So we have how many, 2 terabytes-ish?
The current database is 3.5 terabytes, and that's after we've done some roll-up on the biggest data. So if we hadn't done that, it's probably over 4 terabytes at this point.
Yeah, we have hundreds of millions of HLLs that we keep around. We do AGs on HLLs on the same row counts as people do on raw data. So you can build these pretty quickly. You can union them pretty quickly. It's not a huge issue. Scott, did you have a question?
Oh, yeah. There was a concern raised about the exception safety of Number 3.
Yep.
Also, now the basic implementation doesn't use C++ exceptions. It's only a couple hundred lines, and near as I can tell, it's actually valid C99.
It is valid
So
C99.
you could probably just dump the C++ compiler.
Yeah, so I haven't done that because I don't claim to know how either G++ or GCC or Clang work. So if somebody is really nice and wants to look at that code and tell me how to fix that make file to make it work, well, I'll buy you something. I don't know.
My first thought would be to just rewrite it and straight C.
I think you can probably just copy paste it.
Yeah.
But,
Yeah. Okay. And that was actually going to be one of my questions, which might have that also as an easy solution, which is that. So PostgreSQL is licensed under Apache.
yeah.
Was Murmur 3 licensed under Apache?
It is oddly enough public domain, if I recall correctly.
Oh, okay, that makes things easy.
Yeah. I think I'd point out one last thing. So all the functions, HLL functions that accept something that's not an HLL, so basically if you're saying turn this column into an HLL, they don't actually accept biggins as their input. They accept a special type we built called an HLL hash val, which is a biggin behind, but it forces you to use the hash function because we really didn't want people to put unhashed stuff in there. You can always cast any biggin to an HLL hash file and it won't break. But that's just a point to my previous slide about like some pitfalls. People will use it in ways you don't expect, so try to guide them in the right direction in terms of the best practices of using sketches and make sure they put hashes on top of their inputs and so on and so forth. So that's about it. I'm losing my voice, so I will not take any more questions. But thank you all for coming. Thank you all for eating our pizza. Thank you all for listening to me.
Thank you very much. Awesome. Well, so thanks a lot, everybody. You already got the announcements about next meetup, etc. We don't currently have anything scheduled for November. So if somebody has something they want to present, please contact me. Beyond that, yes?
I just wanted to point out that we are hiring.
Oh, okay. Yes, please give the obligatory hiring announcement.
Okay, so Matt, go ahead and I'll keep
First off, I'm looking for an apprentice.
Matt's a great TBA. He's a joy to work with. He's super smart.
Just one of things for to teach.
Yep. I'll say, so my group is the infrastructure group. We basically build a lot of the plumbing here. So we move all those gigabytes of events around every day. We archive them, we process them, we aggregate them.